Okay, now let's welcome our new topic, that is reliability allocation. So today I'm going to talk about this topic and not just bring it as so much, I don't want to make it lengthy. I just want to make things shorter. So I'll wind up as quickly as I can. Okay, so just not talk about it and start the topic, the reliability allocation. As you know that being an engineer, of course, reliability is the duty of an engineer. Being an engineer, you have two duties to solve. You have two problems to solve. Oh, sorry for the middle thing in between. Sorry. So we have two things to solve, two problems to solve. That is, one is we focus on the design, and the other is the validation. We focus on our design thing, that what is the design of our circuit and how it's gonna work, and the other is the validation, that how that circuit, how much time it would be validated and how much time it's gonna fail and all this. So we focus on these two parameters, on these two things is the main focus of our uh, you can say that of our um, basically it's the main focus of our circuit, of our parameter, of our kind of RBD, that we have to work on this, on the design and validation of our product. Oh yeah, exactly, of an item of our product. So you have to work on these two. So as it's written here, series system composed of k subsystem. As for finding out the reliability allocation, here we have a series system, that is, always remember that it's composed of k subsystems. Reliability allocation would be always in the series system, and we have the series system is composed of k subsystems, and each subsystem is composed of an I element that is also in series. Okay, so we have a system that is in series, and it is composed of k subsystem, and this k subsystem is this subsystem is composed of n of I element that is also in series. It's written here. So we say that when Ti is less than Mi, and what is Mi? Mi is the mean life of the I subsystem. We are talking here about the I element, I system, subsystem, that is the subsystem. We are talking about the I element. So we say that our Ti time I is less than Mi, and Mi is the mean life of that I subsystem. Okay, so we have as we say that above here, that series system is composed of k subsystems. So we have 1 2 3 and so on till k. So this series system is composed of k subsystems. It's all from 1 going to k. Okay, so I told you about this. And what is Wi? Wi is the probability of failure of the I element. I told you that we are talking here about this I element. We are working on this I element. So what is Wi? Wi is the probability of failure. That what is the probability of failing of the I element, like how this I element gonna fail, and what is the probability, what is the chances of failing of this I element, which can be due to the failure of a component and subsystem. Like how this probability, how much is the probability of this I element that is going to fail, which can be due to the failure of a component, or due to the failure of a subsystem. So it's till now. So we have a equation on this thing. We bring out an equation, that is reliability equals to I going from 1 to k. So here's I, and what we talk about I, that is, it is going from 1 to k. We have a subsystem, that is I. We have I element that is going from 1 to k, and 1 minus Wi and 1 minus Ri, the probability of failure of I element. So this is the probability of the failure of an item. Okay, that is 1 minus Wi, that is, it is unreliability of an item that is going to fail, and probability of failure, and this is the reliability, this is the unreliability, and this is the probability of an atom that is going to fail, and I is going from 1 to k. Okay, so what's here, I hope that everything is clear. So Ri, here it is. We say Ri equals to E at the minus Ti over Mi. We create a formula of R of I, that is E going from minus Ti over Mi. Okay, it is because why it is in this way? Because I told you that Ti is less than Mi. So Ti is less than Mi, so that's why Ti is on the above part and Mi is on the lower part. It's exponent in the exponential form, so that's why it's in the above part, in the numerator. Ti is in the numerator and Mi is the denominator, because Ti is less than Mi. Okay, so we bring this formula over here, where it is. Okay, here we keep it here in the replacement of Ri. And what we did next, okay, yeah, come here. This was for when T was less than Mi. Now this is for when Ti is greater than Mi. So what it becomes when Ti is greater than Mi? So this equation, this thing becomes as 1 minus Ti over Mi. This exponent goes away and it comes in the form of like this. When Ti is greater than Mi, so it comes in the form of like this. So by replacing E at the minus Ti over Mi, we create here, we put this thing over here. It's here, yeah. 1 minus in the replacement of Ei, it is like this, and this is multiplication as usual. 1 minus 1 cancels out. So you can understand now that this one is here and this thing is here in the bracket. That's everything is shown in the bracket, so it must be not difficult to understand. Okay, now this one comes here, minus 1 minus Ti over Mi, and this minus, this bracket solves out, and this minus plus 1 and minus 1 goes away, they cancels out, and this minus comes with this minus, becomes in plus, minus minus plus, simple multiplication rule. Okay, sorry for this. Minus minus plus, and everything remains the same. It's really an easy thing and easy subject, I must say. There are kind of short subjects and short topics of reliability. Anything you want, everything is written in the search bar in the description. So if you want any other thing, any other topic, so you can go it from my channel. Anyways, let's forget about it now. So here the equation comes. It's simply it's really observable here. Okay, and what is written here? Let's have a look. I got it. Okay. So where we were, it becomes Wi, Ti and Mi. Okay. So as we did before, you remember that this thing was written in the form of this. We wrote it this as like this. Okay, and now what we did again, we want the equation, we want our equation in the form of exponent. So how we can bring this thing, this 1 minus Wi Ti over Mi in the form of exponent? We can bring it like this. In the form of exponent, we create this in the above part. This thing goes in the exponent form, so minus Wi Ti over Mi. Okay, so I hope this is clear. It's the same thing that we have done in the 2 steps before, you can say that. Okay, now what's the next thing that we are gonna do? So we are saying that our Mi is equals to T over Ni. So this is a formula. We say that Mi over this Mi, you remember this is our mean life of the I component, I subsystem. So this Mi is equals to T over Ni. So let's replace this thing, this Mi into this. So what we get now, it was like in the form of like this, Wi Ti over mi. In the replacement of mi, we keep t over ni. So we got wi ti times ni over t. I hope it's clear to you. It's I'm obviously reading it for you. Wi ti ni over t. Okay, now what's the next? We have t equals, oh sorry, let's not see this. It's done till here, so we put this thing over here. Yeah, you can see that it's the same. Wi ti ni over t, wi ti ni over t, and this minus comes the same, so we create it like this. And one more thing that we can say that we know that these all things, these three characters are constant, so we create a constant here, and we have again a limit of j going from 1 to ni. It's because 1 to ni, it's because you remember we in the above we have a little theory here. We wrote that each subsystem is composed of the ni, I hope you can see that, of ni element that is also in series. So in series we have the product of all components, so that's why we have ni here. So where it is ni, we are putting this limit, that is j going from 1 to ni. First was the I going from 1 to k. This was the each system in series is composed of k subsystems. So we created like this, and then we say that each subsystem is composed of ni element. Okay, and that is also in series. So in series you have the product of all the components, so j going from 1 to ni, and e minus c, it comes from here. We write it like this because we already said that this thing is a constant, so this c is representing the constant, so it comes in this way. And this all, you know, the equation for the r of t, reliability at time t, these things are for this. And now what's next? Now we are coming towards r0. Okay, r0. So what we did for r0, you know that the reliability is at time t, we have all the limits for the reliability at time t, but when we are at the condition of r0, like we have zero reliability, we have when we have zero time, when we are at the condition of 0, so we won't be putting any kind of limits here, we will just be putting the formula here. Okay, so what was the formula that we derived above? It was like e minus wi ti n over, oh, this is a little bit difference in the formula. Why is that so? It is because it's not that difficult. It is that t equals to mi and ni. So why is that t equals to mi and ni? It's just that the things goes here and there, it's just like that, it's not nothing, because in the above part you say that mi equals to t over ni. So if you want to put we create t, so ni goes there and t will become mi and ni, so it's the same here, and we keep it mi and ni here, and this ni comes in n capital. Why it is in capital? Because above we have a limit from we have all the limits we were talking about at time t, and so we have ni, that is I this is j going from 1 to n, and I going from 1 to k. So we were having a limit before, but when we talk about at time 0, like here r0, so we won't be putting any limit. So if we won't be putting any limit, we won't be having any kind of I, so it would just be simple n. Okay, let's say that ni is equals to n, so it would for the at time t we have n small ni, and for r0 we have capital N. And in the replacement of t we keep here mi and ni, so the equation is here, where we can say that rt is equals to r0. So it's kind of same, both are same. And what's next? we have to find out mi, that is the mean life of the I subsystem, I element. So we solve this exponent, oh sorry, not we solved it, it's just that we can write this thing as like this also. So uh, we replace logarithm on the both sides. So by putting logarithm, this exponent goes away, and here it becomes logarithm of r0, and this exponent goes away and this thing comes here. So we have to provide the mi, that is the mean life of the I component. So mi comes here, and this ln r0 goes down there. So how it becomes, it is simple multiplication and nothing else, and rest it's not okay. And the value of mi is wi ti capital N over ni minus ln r0. So this is the value for mi. We create this thing. Okay, what is mi? Mi is m1 is the mean time to failure, m2 is mean time to failure, m3 is mean time to failure. It's simple that mean time to failure, it's just that as in the above we say that mi is the mean life of the I component. In the same way we have m1, m2, m3, that is also the mean time to failure. M is simply the mean time in the failure. Okay, so this thing, this equation can be represented in the form of this RBD. We have 1, 2 and 3, and it can be here we have n1, n2, n3, and here we have w1, w2, w3. w1, w2, w3, it's all written above that what it is, so I'm not going to repeat it. And n1, n2, n3, okay, well, I changed my mind. wi, it's probability of failure of the I element due to the failure of component and subsystem. This is wi, and this is n1, n2, n3. n1, n2, n3, that's the component, I component. So this is the reliability, RBD, sorry. This is starting point and end point. It can be represented like this. So okay, let's just conclude it. And what I can say in the last, that this thing is called the agree method. And what is the agree method? Agree method is basically it has a full form, that is you can see that okay, advisory group of reliability of electronic equipment. So that is the agree method, that is the full form agree method, and that's all for now.